it will also be now the next topic we need to talk about is skewness. So let's say we have this representation of our data. And notice that it is symmetrical. And this line represents the median. And if you have a data that is perfectly symmetrical, the mean, this is the sample mean, it's going to be equal to the median. Now, the box and whisker plot will look something like this. Q2 is going to be right in the middle of Q1 and Q3. So notice that the box plot is evenly distributed. The left side is the same as the right side in length. And also, these lines are equal in length. So that represents a symmetric distribution. Now, what if it's not symmetrically distributed? What's going to happen in that case? There are two possibilities. The data can be skewed to the right, or it can be skewed to the left. So which one would you say this particular shape represents? Would you say it's skewed to the right or skewed to the left? Notice that we have a tail that extends towards the right. So this particular data, or this graph, we say that it's skewed to the right. Now, what is the relationship between the sample mean and the median in this case? So the median, the middle portion of the data, will be somewhere in this region, and the sample mean will be to the right of the median, since it's skewed to the right. So the mean will be greater than the median in this case. By the way, whenever you have a shape that's skewed to the right, some textbooks will refer this as a positive skew. And it makes sense because positive numbers on a number line will be on the right side. Now, you need to be familiar with the box greater than the median in this case. By the way, whenever you have a shape that's skewed to the right, some textbooks will refer this as a positive skew. And it makes sense because positive numbers on a number line will be on the right side. Now, you need to be familiar with the box and whisker plots for this type of distribution. So here's one example. Notice that the right side of the box is longer than the left side. So this tells us that Q3 minus Q2 is greater than Q2 minus Q1. And so in that case, looking at the box and whisker plot, you can see that it's skewed to the right. Now sometimes these two boxes may be equal in length. Nevertheless, this side might be longer than this side. So even if the boxes are of the same length, if this side is longer, it will also be skewed to the right. Now what about if it's skewed to the left? In this case, the graph is going to look something like this. Let me try that again. So notice that the tail is on the left side. So in this case, we have a negative skew, or we could say that is skewed to the left. Now the median will be somewhere in this region, and the mean is going to be to the left of the median, since it's skewed to the left. So the sample mean is less than the median. Now how can we represent this using a box plot? Well, here's one possibility. So in this case, Q2 will be closer to Q3 in the box plot. So as you can see, the left side is longer than the right side. So we can say that Q2 minus Q1 is greater than Q3 minus Q2 in this case. Now, if the boxes are equal in length, you can also tell that we have a negative skew if the left side of the box plot is longer than the right side. So that's another indication that the data is skewed to the left. Now, there's some other things that you need to know if you're going to take a statistics course. And you need to be able to create a dot plot. So let's say if you have the numbers 5, 8, 3, 7, 1, 5, 3, 2, 3, 3, 8, 5. With this information, how can we construct a dot plot? Well, we can begin by drawing a number line. So let's say this is 0, 1, 2, 3, 4, and so forth. We can stop at 8 since 8 is the highest number. Now the first number is a 5. So all we need to do is draw a dot above the number 5. And then let's put the dot 3. Now with them. Don't forget. So let's say we have the numbers 4 and the notification bell. Now let's talk about how we can make a stem and leaf plot. So let's say we have the numbers 4, 9, 13, 13, 17, 21, 36, 38, let's say another 38, and then 56. How can we make a stem and leaf plot with this data? So the first thing we need to do is we need to write two columns. On the left, it's going to be the stem, and on the right, the leaf. So the first number is 4. So for the stem, we're going to write 0. And for the leaf, we're going to put 4. The next one is 9. So we're going to write or represent 9 as 0, 9. So we have 0 on the left, and then we're going to put 9 on the right. The next number is 13. So the first digit is a 1. The second digit we're going to put in the second column. Now we have another 13. So all we got to do is add another 3. Now for 17, we need 1 and 7. We already have the 1, but we need to write the 7 to the right side. Now for 21, we need to put a 2 in the stem column, a 1 in the leaf column. Next we have 36. So we need a 3 in the stem column, a 6 in the leaf column. Now notice that we have 3 38s. So we got to add 3 8s to the leaf column. And finally, 56. Now we don't have anything in the 40s. So we're going to write a 4, but we're not going to put anything here. For 56, we're going to write a 5 in the stem column and a 6 in the leaf column. And so that's how you can make a stem and leaf plot. Now it's always good to have a key. So we could say that 2, 1 represents 21. So if someone looks at the stem and leaf plot, they know what you mean. Let's try another example. So let's say we have the numbers 56. Actually, let's say 78, 85, 89, 92, 106, 107, and 119. Go ahead and make a stem and leaf plot with those numbers. So the first number, 78. We're going to write a 7 in the first column and an 8 in the second column. Next, we have 85 and 89. So we're going to put an 8 for the first digit, and then 5 and 9 for the second. and then it's 92, so we're going to write 9 and 2. Now for 106, we're going to put a 10 in the stem column, but a 6 in the leaf column. And for 107, we just got to add a 7 here. And there's usually no commas, so let's get rid of that. And then finally, for 119, we're going to write 11 in the stem plot and 9 in the leaf column. And so, for example, this will be our key. So this represents 92, and this would represent 106. Because sometimes you could have decimal values. For instance, let's say if we have 1.2, 1.6, 1.8, 2.1, 2.3, 2.3, and 2.5. We can construct this stem and leaf plot like this. So we could start with 1, and to write 1.2, we could just put a 2 for the leaf plot. Now for 1.6, we just got to put a 6 in the leaf column. And for 1.8, just an 8. Now we can move on to the 2's. So we have 2.1, 2.3, 2.3, and 2.5. And so that's how you can make a stem and leaf plot using decimal values. So we can say 1/6 represents 1.6 in this particular example. Now the next thing we're going to talk about is something called a frequency table. So given a data set, how can we make a frequency table? So let's say we have the numbers 5, 9, 8, 7, 8, 12, 9, 8, 10, 8, 9, 7. So using those numbers, how can we make a frequency table? We're going to put two columns. So the first column will represent the number, and the second column will represent the frequency. And let's put down what we have. So the first number is a 5. And how many 5s do we have? There's only one 5, so the frequency is 1. The next number is a 7. And notice that we have two 7s, so the frequency is 2. Next is 8. We have a total of 4 8s, so that gives us a frequency of 4. After that, we have 9. And I've spotted 3 9s. And then there's 1 10. And we have 1 12. So that's a simple way in which you can make a frequency table. Now, here's another question for you. how can we use the frequency table in order to calculate the sample mean? How can we calculate the average instead of just adding all of those numbers up and dividing by the number of data points in a set? Let's add another column. And we're going to call this the sum. We have two 7s. If you add up 7 and 7, you get 14. So 5 plus 14 plus 32 plus 27 plus 10 plus 12, that's 100. And we're also going to add up the frequency column. That's going to give us the total number of numbers that we have here. So we have 1 plus 2, which is 3, plus 4, that's 7, plus 3, that's 10, plus 2, that's 12. So we have a total of 12 numbers. So the mean is going to be the sum divided by the total number of points that we have in our set. So it's 100 divided by 12. So the mean in this example is 8.3 repeated. And so that's how you could use a frequency table to calculate the mean of a data set. Now the next thing that you need to know how to do is how to create a histogram. A histogram looks like a bar graph. But unlike a bar graph, a histogram has its bars connected to each other. So here's an example of a histogram on the left side. On the right side, I'm going to draw a bar graph. So this would be a bar graph. So as you can see, they're very similar, but the bars in a histogram, they're adjacent to each other. There's no space in between. But how do we go about taking a data set and making a histogram? So let's say we have the test scores of students in a typical class. Let's say the test scores are 65, 72, 93, 68, 76, 79, 7.
5 hours. This Excel report took 5 hours to make. Client meeting is in 10 minutes. I can't present this nonsense.
Distribution table. Or rather than describing the frequency of each number. And so what we're going to do this time, rather than talk about how frequent, or rather than describing the frequency of each number, we're going to break it up into categories or classes. On the left side, we're going to have the grade. On the right side, the frequency. Now, I'm going to categorize the grades in levels of 10. So a D would be 60 to 69. A C would be 70 to 79. A grade of a B would be 80 to 89. And an A is going to be 90 to 100. So those are our 4 categories or 4 classes. Now, how many students received a grade between 60 and 69? So notice that there are 2 students. We have the grades 65 and 68. So the frequency will be 2. Now, how many students received a C on their exam? How many students received a grade of somewhere between 70 and 79? So we have 1, 2, 3, and 4. So 4 students got a C on their exam. What about a B? So we have 84, 85, 88, 82, 83, 87. So I counted a total of 6. And what's left over are those who got an A 93, a 98, and a 90. So now that we have our frequency distribution table, we can now make a histogram. So on the y-axis, we're going to plot the frequency. On the x-axis, we're going to put the grades. So the grades will vary between 60, 70, 80, 90, and 100, because the classes are separated by intervals of 10, approximately. Now, the highest frequency is 6, so let's go by 1. 1, 2, 3. Plot out a grade in that region. Between 80 and 89, 6 students fall in that category. And between 90 and 100, only 3 students received an A. So let's put the grade. So this is a D. 2 students got a D. 4 students got a C. And 6 students received a B. And 3 students received an A. So that's how you can create a histogram from a data set like this, using a frequency distribution table. Now, there's something else that we need to go over, and that is making a table with the frequency, the relative frequency, and also the cumulative relative frequency. So let's say we have the numbers 2, 3, 5, 3, 6, 8, 7, 8, 3, 3, 5, 3, 7, 3, 8, 5, 2, 7, 8, 3. So we're going to have We're going to have 4 columns. The first column is going to be the value. The second column will be the frequency. The third column is going to be the relative frequency. And the last one is going to be the cumulative relative frequency. So the lowest value that we have in our list is 2. And notice that we have 2 2s. So the frequency for that number is 2. Next, we have a 3. And we have 1, 2, 3, 4, 5, 6, 7 3s. So that's the frequency. The next number in the list is 5. And we have 1, 2, 3 5s. Now we only have 1 6, which is here. Next is a 7, and there's 1, 2, 3 7s. I need to extend this list. And then finally we have some 8s. 1, 2, 3, 4 8s.
9 rupees. 9 rupees cannot even buy you a packet of chips. But what if I tell you 9 rupees can automate 90% of your work while you are working your Microsoft PowerPoint, Microsoft Excel, or Microsoft...
Now let's have some 8s. 1, 2, 3, 4 8s. Now let's take the sum of the frequency column. So if we add these numbers, 2 plus 7 is 9, plus 3, that's 12, plus 1 is 13, plus 3 is 16, plus 4 is 20. So we have a total of 20 numbers in our set. Now how do we calculate the relative frequency? So for the first entry in that column, take the frequency and divide it by the total number of numbers that you have in the data set. So the relative frequency is basically the frequency divided by n. So for the first one, it's going to be 2 over 20, which is 1 out of 10, and so that's 0.10. For this one, it's going to be 7 divided by 20, which is 0.35 by 20. Next, 0.10 plus 0.35, these numbers, you should get 1. Next, we have the cumulative relative frequency. So we're going to start with 0.10, and then we're going to add these two numbers. 0.10 plus 0.35 is 0.45. Now, 0.45 plus 0.15, that's 0.60. And then if we add 0.60 and 0.05, that's going to be 0.65. And then add in those two numbers, that's going to give us 0.80. And then 0.80 plus 0.20 will give us 1. So that's how you can complete the cumulative relative frequency table given a data set. Now, let's talk about how we could use this information. Using this table, what is the value of the 60th percentile? What would you say? So what we need to do is look at the cumulative relative frequency. So the 60th percentile will end here. Now notice that it's exactly 0.60, which corresponds to 60%. To find the 60th percentile, you need to average these two values. So you have to do 5 plus 6 divided by 2. The average of 5 and 6 is 5.5. And so that's going to be the 60th divided by 60th value. Complete the cumulative relative frequency table given a data set. Now, let's talk about how we could use this information. Using this table, what is the value of the 60th percentile? What would you say? So what we need to do is look at the cumulative relative frequency. So the 60th percentile will end here. Now notice that it's exactly 0.60, which corresponds to 60%. To find the 60th percentile, you need to average these two values. So you have to do 5 plus 6 divided by 2. The average of 5 and 6 is 5.5. And so that's going to be the 60th percentile. Now what about the 80th percentile? So notice that we have exactly 0.8 in the cumulative relative frequency column. So what we're going to do is we're going to average these two numbers. The average of 7 and 8 is 7.5. Now what if it's not listed in the cumulative relative frequency table? For instance, let's say if we have, or if we want to find the 20th percentile. What value corresponds to that? Now the 20th percentile is between 0.10 and 0.45. It's important to understand that after 0.10, you're going to exceed the value of 2. You're going to go into the 3s. And after 0.45, you're going to move from the 3s to the 5s. So the 20th percentile, because it's more than 2, but less than 3, it's going to be 3. There's no numbers in between here if you look at the data that we have. So the 20th percentile is going to fall in this number. To explain it better, it's important to understand that between 0 and 0.10, the value is 2. Between 0.10 and 0.45, the value is 3. Now, if your percentile falls between 0.45 and 0.60, not including 0.45 and 0.60, but if it's between those numbers, then it's going to be 5. It's going to be 6 if it's between 0.60 and 0.65. And it's going to be 7 if it's between 0.65 and 0.8. So let's say if we want to determine the 75th percentile. The 75th percentile is between 0.65 and 0.8. So because it's more than 0.65, we're not going to have the value 6. We're going to get 7. So that's going to be the 75th percentile. Now, let me help you to see this visually so that it makes more sense. Let's begin by arranging the numbers in increasing order. So we have 2 2s. We have a total of 7 3s. And we have 3 5s, 1 6, 3 7s, and 4 8s. Now I'm writing these in pairs of 2s, and you'll see why. We have a total of 20 numbers. And if you take 20 and divide it by 2, you're going to get 10 equal parts. So this is going to be the 10th percentile. Let me put that in a different color. So here's the 10th percentile, the 20th percentile, the 30th, and so forth. So this would be the 100th percentile. There's nothing higher than that. So the first thing that we went over was the 60th percentile, which is here. So notice that we have a 5 on the left and a 6 on the right. So we need to average 5 and 6. And so we said the 60th percentile was 5.5. The second one was the 80th percentile, which is here. Notice that it's between 2 different numbers, 7 and 8. So if we average 7 and 8, it will give us 7.5. Now after that, we talked about the 20th percentile. And the two numbers that it's between are identical to each other. So therefore, the 20th percentile is just 3. And the last one was the 75th percentile, which is between 70 and 80. And so these two numbers are just 7. And so the 75th percentile has to be 7. So now you can visually see the values that correspond to the different percentiles. And if you want to, you could put 0 as well. I forgot to do that. But that's basically it for this video. So hopefully I gave you a good introduction into statistics. There's a lot of other stuff that you'll learn in this course, but these are just some of the basics. Thanks again for watching.
Artificial intelligence and machine learning are at the heart of the digital revolution. Chandigarh University has teamed up with IBM, a global leader in AI technology, to offer computer science engineering honors. With a specialization in artificial intelligence and machine learning, explore the entire spectrum of AI from foundational principles to...
So what is statistics? Statistics is basically the science of collecting, analyzing, and interpreting data, even presented it as well. And statistics can be broken down into 2 categories. On the left, we have descriptive statistics, and on the right, inferential statistics. So let's focus on descriptive statistics first, because you're going to learn that first before you learn inferential statistics. In descriptive statistics, you're basically organizing and summarizing data using numbers and graphs. For instance, you could summarize your data using a bar graph, which looks like this. Many of you have seen this in middle school or high school. You could even organize your data into a histogram. A histogram looks like a bar graph, but the bars are basically attached to each other. So that's the difference between a histogram and a bar graph. You can also organize your data into a pie chart. And this is very useful if you want to break it down into categories based on percentages. Now there's other graphs too. You can organize it using a line graph. You can also use tables to organize your data. You could use a frequency table, a frequency distribution table, and there's a lot of different ways of organizing it. And so that falls under descriptive statistics. You can also describe the shape of the graph. For instance, is the data symmetrical? Or is it skewed to the right? Or is the data skewed to the left? So that all falls under descriptive statistics. Now we can also describe our data using numbers. So for instance, under measures of central tendency, we have things like the mean, the median, and the mode. Now there's 2 types of means that you want to be familiar with. The first one is the sample mean, which is basically a sum of your sample data divided by the number of data items in your sample. The second is the population mean, which is also the sum divided by the number of data items in the population. And the mean is basically the average. The median is the middle number in the sample data divided by the number of data items in your sample. The second is the population mean, which is also the sum divided by the number of data items in the population. And the mean is basically the average. The median is the middle number of a data set, and the mode is basically the number that occurs most frequently. So that's another way you could describe your data, using those types of numbers. You can also describe it in terms of a range, variance, and standard deviation. Now let's move on to inferential statistics. So in this branch of statistics, that's when we take our sample data and we use it to make an inference or even draw a conclusion of the population. We can even use probability to determine how confident we can be that the conclusions that we make are correct. So let's use an example to illustrate this. Let's say in city XYZ, the population is 100,000. Now let's say we wish to make a test. How many people in the city like blue cars? How can we find the answer to this question? Now, it would be unreasonable for us to ask every citizen in the city if they like or if they prefer to purchase a blue car, because that means you have to ask 100,000 people, and that's just not practical. So instead, what we could do is take a small sample of the population, let's say 100 individuals, and ask them, hey, do you prefer to drive a blue car or do you prefer to drive a red car? And see who say yes. Now, let's say if 20 out of the 100 people in our sample says yes. So that means that 20% of people prefer blue cars. This is based on our sample. That's our sample data. So that would fall under the realm of, would you say descriptive or inferential statistics? Which one? Now, this is basically a fact. We're presenting data. So 20 people out of 100 say they like blue cars. So that would be descriptive. Now, we can use that information to draw a conclusion about the population. We can say that 20% of the entire population, maybe within a 2% margin of error, like blue cars. In this case, because we're making an inference or we're drawing a conclusion, that will fall under inferential statistics. Now, there's something known as confidence intervals, which also falls under inferential statistics. So we could say that we are 95% certain or 95% confident that 20% of the individuals living in city XYZ prefer to drive blue cars within a 2% margin of error. Now, we can increase our confidence and get a better picture of the population data and how they like blue cars if we increase our sample size. So let's say we increase it to 1,000 instead of 100. So if we ask 1,000 people, do they like blue cars? And let's say the data is now different. Let's say 21% says yes to it within a 1% margin of error. So this value is going to be a better reflection of the population in response to their preference for blue cars because our sample size is bigger. So now we can say that 21% of the population prefer blue cars within a 1% margin of error. So by increasing the sample size, you can make a better prediction of the population and their preference for blue cars. And so that's a basic intro between descriptive statistics and inferential statistics. So hopefully this video gave you a better understanding of these two topics. So that's all I got. Thanks for watching.
If you're someone who procrastinates a lot, no matter how hard you try, but you cannot get things.
In this video, we're going to talk about data and the different types of data. As you can see, we have it on the board. There's two types, quantitative and qualitative. When you hear the word quantitative, what do you think of? I think of numbers, such as 5, 8, 12. That's quantitative data. It's numerical data. And there's two types of numerical data. You have the form that is discrete and the form that is continuous. Now, discrete data, it's based on counting. For instance, let's say if there are 8 cats, that's a discrete number. You cannot have 8.5 cats. That's not possible. You can't have 2.37 cats. And so when you're counting, let's say animals or objects, it's based on whole numbers or 0 as well. But you can't have any number in between. You can't have 7.46 cats. So counting is based on a discrete numerical data. Now, something that can be measured is based on a continuous form of numerical data, such as distance. The distance between point A to point B, it doesn't have to be an integer. It doesn't have to be 5 meters or 8 meters. It could be somewhere in between. It could be 5.56 meters. It could be 7.283 meters. And so it doesn't have to be a whole number or an integer. It can be any number in between. So that would be a type of continuous numerical data. So to review, remember this. Anything that can be counted would fall in the category of discrete data, which is also quantitative. And anything that can be measured is continuous data, which also falls under the category of quantitative data. So things like distance, speed, weights, these are numbers that can be measured, or these are properties that can be measured with numbers. Now let's move on into qualitative data. Qualitative data is basically descriptive data based on observations. And you use words to describe this data, not numbers. And that's a key difference between quantitative and qualitative data. Quantitative data use numbers, qualitative data use words. Now, qualitative data usually involves the 5 senses. It can be visual, like what you see, such as color. It can be feel. Does something feel soft or hard? It can be taste. That food tasted good, or maybe that one tasted bad. It can be what you hear. Is the volume low or is it high? That's descriptive data. What about the smell? Does it smell good or smell bad? Or does it smell at all? So these are different forms of qualitative data. And as you can see, you use words to describe it. Now let's see if you remember what you've learned. What I'm going to do at this point is I'm going to quiz you. And I'm going to give you some situations. And I want you to determine, is it quantitative or is it qualitative? And if it is quantitative, would it fall under the category of being discrete numerical data or continuous numerical data? So let's say if we have 7 dogs. Is that quantitative or qualitative? Well, in this case, we're dealing with a number, so that would be quantitative. Now, are we dealing with discrete data or continuous data? The visual senses, we're seeing the color, and we are describing it using words, so this would fall under the category of qualitative data. Now, let's say that Michael is 6 feet tall. So this 6 feet, his height, is it quantitative or qualitative? So we're dealing with numbers. That is quantitative. Now, is it inches tall? Measurement, it is a form. Now, let's say it doesn't have to be exactly 6. So because this involves measurement, it is a form of continuous. Let's say
Xiaomi 14 CV with Leica professional cameras. Make it cinematic.
Your American dream, now a reality with a 1-year STEM Masters. Graduate with a...
In this video, we're going to talk about the differences between a statistic and a parameter. But first, what do you think the difference is between the two? Statistics are characteristics that describe a sample. Parameters are characteristics that describe the population. Now, you need to know the difference between a sample and the population. The population will represent everyone or everything in a study. The sample is basically a subset of the population. It's a small portion of the population. So let's say in town XYZ, we have 100,000 people. And let's say we wish to estimate the average age of the 100,000 residents in town XYZ. Now, it's going to be a lot of work to get the age of each individual and average all of their ages. But instead, let's say if we talk to 100 individuals out of the 100,000, ask for their ages, and then take the average. So the average age of those 100 individuals would be the sample mean. So that is a statistic. The true average age of all of the 100,000 residents of town XYZ, that would be the population mean. That's a parameter. So the sample is a small subset of the population. The population is 100,000, but the sample that we chose is only 100 individuals out of the population of 100,000. So hopefully that helps you to see the difference between a sample and a population. Now let's talk about some variables that would also highlight the differences between statistics and parameters. So this symbol represents the sample mean. So that would be a statistic because it describes the mean of the sample. That symbol, mu, is the mean of the population. That's a parameter. It's a characteristic of the population. S stands for the standard deviation of a sample. So that would be a statistic. Sigma is the standard deviation of the population. That's a parameter. S squared represents the sample variance. Sigma squared is the variance of the population. So that's a parameter. Next, we have proportions. The sample proportion is simply p hat. And the population proportion is simply p. Finally, we have the sample size. Well, let me just say the size. The size of the sample is represented by the symbol lowercase n. So that would be a statistic. The size of the population is represented by the symbol capital N. So that is a parameter. So hopefully, these symbols will help you to see the difference between a statistic and a parameter. Now let's take a brief quiz. So for each of these statements, determine if it describes a statistic or a parameter. Number 1, the average weight of all males in the United States. Is that a statistic or parameter? What would you say? Now remember, a parameter would describe everyone in a group. A statistic would describe only some of the individuals in a group. So for number 1, we're dealing with the weight of all the males in the US. So that is a parameter. Number 2, the average height of 100 cats in the state of California. California have millions of people, and in the whole state malls, because in the so the average test in the same studio. So now you know the difference between a statistic. The symbol would be X bar to represent the sample mean population.
Are you a student who learns from YouTube videos or attends online classes? Video Notebook will make...
In this video, we are going to talk about the different scales of measurement found in a typical statistics course. And it's basically the different ways in which a set of data can be measured. So the first type is the nominal scale data. And basically this form of measurement is more on the qualitative side. It has less to do with numbers. The second one is the ordinal scale data. The third one is the interval scale data. And finally, the ratio scale data. So let's talk about the first one, the nominal scale data. So as we said before, this is a qualitative form of measurement. It's categorical, so it can include names, colors, labels, and things like that. So for instance, we could assign a 1 to the color red, 2 to the color blue, 3 to, let's say, the color green, and the order in which we place it really doesn't matter. Red doesn't have a higher quantitative value than blue. It's all arbitrary. So it really doesn't matter which way we order it. Blue could be number 1 or green could be number 1. It really doesn't matter. And so as you can see, these qualitative forms of data cannot be used in calculation. However, the responses of people to these different colors, for example, can be used in calculation. Here is an example. So let's say if we do a survey and we ask 10 individuals, what's their favorite color? Let's say 5 chose red, let's say 3 chose blue, and 2 chose green out of a total of 10. So in terms of percentages, out of that small survey, 50% preferred red, 30% preferred blue, 20% preferred green. So that's one way in which we could use this form of data in calculation. But the individual colors themselves, red, blue, and green, they can't be used in calculation on their own merit, since it's a qualitative form of data. Now make sure you understand this. For nominal scale data, the order doesn't matter. But as you can see, for the other types of data, the order does matter. So let's talk about the second one, the ordinal scale data. So this type of data is typically used to rank, basically, things. Let's say if you have a race. There's a first place winner, there's a second place winner, and there's a third place winner. In this case, this would be an ordinal scale data, because the order matters. However, the differences cannot be measured. The difference between first and second place is not the same as the difference between second and third place. Now, so this type of data is typically used to rank, basically, things. Let's say if you have a race. There's a first place winner, there's a second place winner, and there's a third place winner. In this case, this would be an ordinal scale data, because the order matters. However, the differences cannot be measured. The difference between first and second place is not the same as the difference between second and third place. Now, if you're looking at numbers, 2 minus 1 is 1, 3 minus 2 is 1. But that's not the way in which we should really look at it. To illustrate this, we could say that in a race, the person who got first place, let's say he took 4 minutes and 53 seconds to arrive at his destination. And let's say the person who was in second place took 4 minutes and 55 seconds. So as you can see, the time for these two individuals is very close. Now, the third place winner, he might have taken a longer time. Maybe he took 6 minutes and 2 seconds. And so the difference between the first and the second place winner is much different than the difference between the second and the third place winner. And so if you don't have the time, you can't really use this data to measure the difference. So this is an ordinal scale data, because differences cannot be measured unless you're given this data. So let me give you another example of an ordinal scale data. So let's say if we're ranking experiences, and let's say the options are excellent. The second one is, let's say, good. The third is satisfactory. And let's say the last one is just bad. In this case, we can't really measure the difference between excellent and good. However, we can assign them values. We can give excellent a value of 1, good a value of 2, satisfactory a value of 3, and bad a value of 4. So here, the order makes sense. Excellent is the best, so number 1 has the highest value. Bad is the worst, so number 4 has the least value. But we can't really measure the difference between excellent and good versus good and satisfactory. We just know good is better than satisfactory, and excellent is better than good. But to measure the difference, that's not really possible in this case. So this would fall under an ordinal scale data. Now let's move on to the next form of data. So that is the interval scale data. So for this one, the order does matter, and differences can be measured. For the last one, we said that differences cannot be measured. To illustrate this, temperature is a good example. So let's say if we have two temperature values, 30 degrees Fahrenheit and 60 degrees Fahrenheit. And let's say 90 degrees Fahrenheit. So the difference between a temperature at 30 and a temperature at 60 can be measured. That's a difference of 30 degrees. And the difference between 60 and 90, that can be measured as well. That's another change of 30 degrees Fahrenheit. So differences can be measured for the interval scale data. However, ratios, you can't measure the ratios for this form of data. So what do we mean by that? 60 degrees is not 2 times as hot as 30. If you divide 60 by 30, you get 2. But a temperature of 60 degrees Fahrenheit doesn't mean that it's twice as hot as a temperature at 30 degrees Fahrenheit. It doesn't work that way. And so we can't really measure ratios with an interval scale form of data. Now the next thing that we need to talk about is number 3. There is no true zero starting point. 0 degrees Fahrenheit is not the lowest temperature. It's not the absence of heat, because you could have negative values. The temperature could be negative 20 degrees Fahrenheit. It could be negative 40 degrees Celsius, which also makes it an interval scale data. Now, if you're dealing with units of Kelvin, that's a whole different story, but for units of Fahrenheit and Celsius, there's no true zero starting point, since you can have negative values. Now, going back to number 1, the order matters because you can place these temperature values in order. 30 is lower than 60, and 60 is lower than 90. So you can place that in increase in order. So in that sense, the order matters for this form of data. Now let's talk about the last one, the ratio scale data. So for this one, the order matters as well. Differences are measurable, including ratios, and it does contain a true zero starting point. So let's use grades. Let's say the grades that you'll get on a typical statistics exam. Let's say we have the numbers 70, 30, 56, 82, and 90. So the order matters because we can arrange it in ascending order. So we can write it as 30, 56, 70, 82, 90. And the order has meaning. This is the lowest grade, this is the highest grade. Now the differences can be measured. For instance, 56 minus 30 is 26, and 70 minus 56, that's 14. So as we can see, the differences are measurable. And we can also measure the ratios. If we take 90 and divide it by 30, we get 3. And so we could say that this student has a grade that is 3 times higher than this student with the lowest test score. And that would make sense. We can see that the ratios, they're meaningful. And the last thing is true. It does contain a zero starting point. Let's say if we have another student who didn't answer any questions, he would have a grade of 0. So that means that either he didn't do the test or he did the test but got all the questions wrong. And so this, it has a meaning, it has a value. It means that he didn't get anything right or just didn't do anything. And you can't have a score lower than 0. You can't have a test score of negative 20. And so in this case, a 0 is a true starting point for this form of data. Let's take a minute and summarize what we've just learned in this video. All 4 forms of data can be labeled. So let's put a check mark for that. Now, the nominal scale data doesn't have any meaningful order. The order doesn't matter. But for the other 3 forms, the order does matter. Now, we can only measure a difference for the interval scale data and the ratio scale data. The nominal and ordinal scale data, we can't measure a difference. Now, the only one with a true zero starting point is the ratio scale data. For the rest, it's not applicable. And so that's it for this video. That's all I got. Thanks again for watching. Peace. In this video, we're going to focus on calculating the mean, median, mode, and range. So let's begin. Let's say if we have the numbers 12, 7... Well, let's write some equations. The average will be 90. Let's say if you're given a set of... Let's say if you're given a set of values, and you want to find the missing value if you're given the mean. How would you do it? Well, in this problem, that's exactly what we need to do. Kristen received the following scores on the first 4 chemistry exams. She got an 82, 89, 85, 96. What score will she need to get on her next exam to have an average test score of 90? So what we have is, there are 5 exams. The first exam, she got an 82. On the second, she got an 89. On the third, she got an 85. On the last one, the 4th exam, she got a 96. Now, we want to know the missing value, or the value of her 5th exam, such that the average test score is X value. Or, so that's what we have. Kristen needs to get, this is the grade that she, to get an easy, these 4 values is going to be get with, and it's X1 here. In this video, we're going to be focused on solving problems that ask us to find either the weighted mean or the weighted average. So let's begin. In this video, we're going to be focused on solving problems. In this video, we're going to be focused on solving problems that ask us to find either the weighted mean or the weighted average. So let's begin with this problem. So we want to calculate the weighted mean of the sample of numbers shown below. Well, first, let's calculate the mean of those numbers. The sample mean is basically the sum of all of the x values divided by the number of values that we have in a list. So it's going to be 16 plus 20 plus 12. And we have a total of 10 numbers, so n is 10. Now let's get the sum of those 10 numbers. So the sum, a sample mean of 17. Now, there's another way in which we can get this answer. So times the sample, then or more specifically the weighted divided by 10 numbers, that gives us a sample mean of 17. Now, there's another way in which we can get this answer. So we can also calculate the mean, or more specifically the weighted mean, if we take the sum of all the weights times the sample. The weight could be in the form of frequency, or it could be in the form of a percentage, and then divided by the sum of the weights. So looking at the first number, we're going to start with the lowest number, that's 10. The next times weights, 20 is 10 plus 12, the same sum of 170. Now let's look at another example. In a class of 20, 8 students averaged a score of 86. 7 students had an average of 74, and 5 students had an average test score of 98. What is the average test score for the entire class? We're going to use the same formula to calculate the weighted mean. So it's going to be the sum of all the weights times each data in our sample, divided by the sum of all the weights. So first, we have a weight of 8 students and an average score of 86. Next, we have 7 students, so that's the frequency or the weight, and the average for that is 74. And then we have 5 students with an average test score of 98. Now we need to divide it by the sum of the weights. So 8 plus 7 is 15, plus 5 gives us the total of 20. So let's do this one step at a time. First, let's multiply 8 by 86. That's going to be 688. Next, we have 7 times 74. That's 518. And then 5 times 98, which is 490. So taking the sum of those three numbers, 688, 518, and 490, we have a sum of 1696. Dividing that by 20, students have an average weight of 140 pounds. 35% of students have an average weight of 160 pounds. 30% of students have an average weight of 175 pounds. And 15% of students have an average weight of 195 pounds. All right, so that's a lot of information. But based on this data, what is the average weight of all students in this high school? So based on the last two, previous problems, W the 40, the second 3, next 4, and get the answer 4 in this high school. Calculate the final semester grade of John and Kelly. So we're going to use the same formula to do so. It's going to be the sum of the product of the weight, since we have of all, or 1 as a decimal. And the homework score for 20, Kelly's home score is 82. About why? Calculate the GPA, or the grade point average of the student. So we're going to use volume 20%. So this is the solution of that solution. Now, total volume now here can act up. It has issues. Solution, iteration of that solution. Now, if you were to average 20 and 50, assuming they have equal weights, the midpoint of 20 and 50 is 35. Now, because the weights are not equal, we know the answer won't be 35. But is the answer closer to 20% or is it closer to 50%? What would you say? So take a minute and think about that. Will the average concentration, the new antifreeze concentration, will it be between 20 and 35 or 35 and 50? Now, notice that solution 2 carries more weight than solution 1. Therefore, the combined solution should have a concentration somewhere between 35 and 50. And so I'm going to write that. It should be somewhere between 35 and 50%, because solution 2 carries more weight than solution 1. So it's going to be closer in concentration to solution 2. So now let's calculate the weighted average, or the new concentration of the antifreeze solution. So it's going to be the sum of the weights times, in this case, the concentrations, divided by the sum of the weights. So it's going to be W1, X1, 8 times 50, so that's percent. It's between 35 solutions.
Did you know you can AFK Bloods and Zaya whilst learning to code in Python? Go to boot.dev. We've known our students to pull it off. Here's how. Monitor 1, code. Monitor 2, level rune crafting. Before you know it, you'll have written thousands of lines of real code and even knocked out that Karamja Elite Diary rune crafting requirement. It's well known that developers make bank and work remotely, but only slightly less well known is that you'll never have to be bored while learning to code these days. No lengthy video lectures required. We won't tell you it'll be easy. It won't be, but it is fun, even addicting if you love computers and puzzle solving.
Today, we're going to talk about about the arithmetic mean, the geometric mean, the weighted mean, and the harmonic mean. In addition to that, the root mean square formula as well. So if you want to calculate the arithmetic mean, or if you want to find the average, what we need to do is take up the sum of a series of numbers and divide it by the number of numbers that you have, or the number of observations. So this would be like x1 plus x2 plus x3 all the way to xn divided by n. So that's the formula to calculate the arithmetic mean. Now let's say if we have an arithmetic sequence. Let's say we have the numbers 2, 5, 8, 11, 14, 17, and 20. The first term is 2, the second term is 5, the third is 8, and so forth. Each term is separated by a common difference of 3. Now it turns out that if we were to take 8, it's going to give us, so let's get 14 plus 17, first, 2 is the middle number, 2 plus 8. So let's average the first and the fifth term. The average of 1 and 5 is 3. 1 plus 5 is 6, divided by 2 is 3. So this will give us the third term. So a sub 1, the first term is 2. A sub 5, the fifth term is 14. And let's divide that by 2. So 2 plus 14 is 16. 16 divided by 2 is 8, which gives us the third term. I want you to understand this process and how the arithmetic mean relates to an arithmetic sequence. So if we want to find the arithmetic mean of the second term and the seventh term, we're going to get the term in the middle, which is going to be, actually, let's do the third term and the seventh term. The term in the middle is going to be the fifth term. The arithmetic mean relates. I want you to understand this process and how the arithmetic mean relates to an arithmetic sequence. So if we want to find the arithmetic mean of the second term and the seventh term, we're going to get the term in the middle, which is going to be, actually, let's do the third term and the seventh term. The term in the middle is going to be the fifth term. So we should get 14. So a3 plus a7 divided by 2. The average of 3 and 7 is 5, so we should get the fifth term. a3 is 8, a7 is 20. 8 plus 20 is 28. 28 divided by 2 is 14, which equals a sub 5. So that's how the arithmetic mean works in an arithmetic sequence. Now let's move on to the next topic. The arithmetic 2. So 2 plus and 10, second term. The arithmetic mean of 1 and 3 is 2. 2 is the middle number of 1 and 3. So this is going to give us the second term. So if we were to average 2 and 8, this would be 2 plus 8 divided by 2. 2 plus 8 is 10. 10 divided by 2 is 5. That will give us the middle term. Likewise, if we were to take the arithmetic mean of the first term and the fifth term, we will get the term in the middle, which is the third term. So let's average the first and the 17 plus 20. And we have 7 observations, or 7 numbers. So let's divide that by 7. So the sum of the 7 numbers that we have is 77. And 77 divided by 7 is 11, which gives us the middle term. So that's a quick and simple way to find the arithmetic mean of the 7 numbers. Now, notice what happens if we find the arithmetic mean of the first and the third term. The arithmetic mean of 1 and 3 is 2. 2 is the middle number of 1 and 3. So this is going to give us the second term. So if we were to average 2 and 8, this would be 2 plus 8 divided by 2. 2 plus 8 is 10. 10 divided by 2 is 5. That will give us the middle term. Likewise, if we were to take the arithmetic mean of the first term and the fifth term, we will get the term in the middle, which is the third term. So let's average the first and the fifth term. The average of 1 and 5 is 3. 1 plus 5 is 6, divided by 2 is 3. So this will give us the third term. So a sub 1, the first term is 2. A sub 5, the fifth term is 14. And let's divide that by 2. So 2 plus 14 is 16. 16 divided by 2 is 8, which gives us the third term. I want you to understand this process and how the arithmetic mean relates to an arithmetic sequence. So if we want to find the arithmetic mean of the second term and the seventh term, we're going to get the term in the middle, which is going to be, actually, let's do the third term and the seventh term. The term in the middle is going to be the fifth term. So we should get 14. So a3 plus a7 divided by 2. The average of 3 and 7 is 5, so we should get the fifth term. a3 is 8. a7 is 20. 8 plus 20 is 28. 28 divided by 2 is 14, which equals a sub 5. So that's how the arithmetic mean works in an arithmetic sequence. Now let's move on to the next topic. The geometric mean. So let's start with a geometric sequence. Let's say we have the numbers 3, 6, 12, 24, 48, 96, 192. First, I want you to see the difference between an arithmetic sequence and a geometric sequence. So going back to the arithmetic sequence that we had before, to go from the first term to the second term, we need to add 3. So the common difference is 3. To get each successive term, you have to add 3. With a geometric sequence, you're dealing with multiplication. Instead of a common difference, you have a common ratio. In this case, the common ratio R is 2. We need to multiply by 2 to get the next successive term. So that's the defining characteristic of a geometric sequence. Now you might be wondering, what is the geometric mean? So recall that taking the arithmetic mean of 2 and 8 gave us the middle number 5 in the arithmetic sequence. What just happened there? Taking the arithmetic mean of 2 and 14 gave us the middle number in the sequence, which is 8. The same is true for finding the geometric mean in a geometric sequence. So this is a sub 1, a sub 2, a sub 3, a sub 4, and so forth. The geometric mean of two numbers is the square root of the product of those two numbers. So if we want to find the geometric mean of, let's say, a1 and a3, we're going to get the middle term, a2. So a1 is 3, a3 is 12, 3 times 12 is 36, the square root of 36 is 6, which is the value of a2. So let's say if we want to find the geometric mean of a1 and a5, the middle term between a1 and a5 is a3, so we should get that answer. a1 is 3, a5 is 48, and I'm going to use a calculator for this. 3 times 48 is 144, and the square root of 144 is 12, which is the value of a3. So that's how you define the geometric mean between two numbers. You could simply use this formula. It's the square root of the product of those two numbers. But now sometimes you may want to find the geometric mean of many numbers, not just two. In this case, you could use this formula. It's going to be two numbers. You could simply use this formula. It's the square root of the product of those two numbers. But now sometimes you may want to find the geometric mean of many numbers, not just two. In this case, you could use this formula. It's going to be the product of those numbers, x1, x2, times x3, times x4, all the way to x sub n raised to the 1 over n. So let's say we want to find the geometric mean of these 7 numbers. By the way, so this formula comes from this equation, because if you have just the two numbers, the first two data points, this would be x1 times x2, and since we have two numbers, it's going to be 1 over n or 1 over 2. And when you raise something to the 1/2, it's the same as finding the square root of that thing you're looking for. So these two formulas are identical, but if you have multiple data points, then this equation becomes extended. So x1 is 3, x2 is 6, x3 is 12, and so forth. And we'll go all the way to 192. So we have 7 numbers here, so we're going to raise this to the 1 over 7. So 3 times 6 times 12 times 24, all the way to 192. I'm just going to do this one step at a time. I get 4, 5, 8, 6, 4, 7, 1, 4, 2, 4. I'm going to raise that to the 1/7 power, and I get 24. Notice that this is the middle term in the geometric sequence of 7 numbers. So when I took the arithmetic mean of the first 7 terms, I got the 4th term because that's the middle term. Likewise, taking the geometric mean of all 7 terms in the geometric sequence gave us the middle term of that sequence, which is the 4th term. So I want you to see how the arithmetic mean, how it works in an arithmetic sequence of 7 numbers. So when I took the arithmetic mean of the first 7 terms, I got the 4th term because that's the middle term. Likewise, taking the geometric mean of all 7 terms in the geometric sequence gave us the middle term of that sequence, which is the 4th term. So I want you to see how the arithmetic mean, how it works in an arithmetic sequence, and how the geometric mean works in a similar way when dealing with a geometric sequence. But this is the formula that you want to use to calculate the geometric mean if you have many data points. If you just want to find the geometric mean of 2 numbers, you can simply use that formula.
Did you know that a major tech company faced a downtime loss of $1.7 million per minute? How did they solve it? With the help of...
Now let's move on to the next topic. So let's talk about how to calculate the weighted mean, or the weighted average. Here's a formula that you can use to calculate it. So the weighted average is going to be the sum of the products of the respective weight, which typically will be like a percentage, times the x value. And then once you add those up, we're going to divide it by the sum of the weights, or the percents. Another way to see this formula would be like this. So W1 x1 plus W2 x2 plus W3 x3, and then plus Wn xn. All of this is going to be divided by W1 plus W2 plus W3, all the way to Wn. Now, typically, you'll see this formula. It's going to be used for situations like calculating the center of mass. That's basically a weighted average, or calculating the acid concentration of a mixture, or even, let's say, average atomic mass. Those are some topics in chemistry and physics where you would typically use the weighted mean to get it. But what I'm going to do is use the example of the acid mixture. So let's say if we have solution 1, let's say this is a sodium chloride salt solution, and the concentration, let's say it's 20% salt, and the volume of the solution is 150 milliliters. And what we're going to do is we're going to mix it with another solution, but with the same substance. So this is another sodium chloride solution. This one's going to be more concentrated, so it's going to be a 40% solution, but the volume's going to be lower. So we only have 50 milliliters of solution, but we're still dealing with the same substance, sodium chloride. If we were to combine those two to form a larger solution, basically if we just mix those two together, what will be the concentration of the new solution? The identity of the solution will still be the same, but what's the new concentration? We know that if we add 150 milliliters of liquid with 50 milliliters of liquid, the total amount of liquid that we will now have is 200 milliliters. But what will be the new concentration? In this case, we could use the weighted average formula. So let's start with this formula again. We know W1 x1 plus W2 x2 divided by W1 plus W2 will give us the weighted average of x. In this problem, x is going to be the concentration. The weight is going to be the... Let's briefly review the arithmetic mean formula. We know the average is going to be the sum of all the data points divided by n. Or in other words, to find the arithmetic mean, we can add up all of the x values, x1 plus x2 plus x3, all the way to x sub n, and then divide that by... We're going to divide it by the number of observations of the... So let me show you what I mean. So instead of summing n, and then divide that by the number of observations, to calculate the harmonic mean, we need to take the reciprocal of the way in which we would calculate the arithmetic mean. So let me show you what I mean. So instead of summing all of the x values, we will take the sum of the reciprocal of the x values. Now, once we have the sum, we're going to divide it by the number of observations. In the calculation of the harmonic mean, we need to do the same thing. Once we have the sum of all of the reciprocal of the data points, we're going to divide it by n. Now, there's one additional step. With the harmonic mean, we need to take the reciprocal of our final result, or raise it to the negative 1 power. Which means you could rewrite the formula like this. So if we were to flip this fraction by applying the negative 1 exponent, it becomes n over the sum of the reciprocal of the data points. So this is how you would calculate the over the sum of the reciprocal of the data points. So this is how you would calculate the harmonic mean. But I wanted to show it to you this way so you can see how it relates to the arithmetic mean formula. So if you want to calculate the harmonic mean of multiple data points, it's going to be n divided by 1 over x1 plus 1 over x2 plus 1 over x3 all the way to 1 over xn. So this equation is simply the expanded form of that equation. Now, earlier in this video, we talked about how we could use the arithmetic mean formula to calculate the middle term in an arithmetic sequence. And we could also use the geometric mean formula to calculate the middle term in a geometric sequence. Well, it turns out that it works the same way with the harmonic mean formula. You could use that formula to calculate the middle term in a harmonic sequence.
I see you're interested in learning about Postgres. Why not learn from me, Dr. Chuck? I'm a professor at the University of Michigan, and I teach the most popular online Python course on the planet.
So let's say if we have the sequence 1 over 2, 1 over 5, 1 over 8, and so forth. Now, notice that the denominators of these fractions, if you just look at the numbers 2, 5, 8, 11, 14, 17, they form an arithmetic sequence. But once you take the reciprocal of the data points in an arithmetic sequence, what you now have is a harmonic sequence. So this is a sub 1, a sub 2, a sub 3, all the way to the 7th term. Well, we should probably use a different letter than a, because a usually is associated with arithmetic. So since this is not an arithmetic sequence, it's a harmonic sequence, let's use h sub 1, h sub 2, and so forth. I probably should have used G instead of A for the geometric sequence, but you could change that, if you want to. Now, if we want to take the arithmetic mean of two numbers, we know it's the sum of those two numbers, a plus b, divided by those two numbers. So instead of writing n, we can just write 2. If we want to take the geometric mean of two numbers, it's the square root of a times b, and this has the index number 2. Well, if we want to take the harmonic mean of two numbers, it's going to be 2 over 1 over a plus 1 over b. So going back to this formula, where the harmonic mean is n over the sum of 1 over x, if we have two numbers, n is 2, and then this is just 1 over x1 plus 1 over x2. So as you can see, these two formulas are the same. It's just instead of x1 and x2, I'm using a and b. So this is how you would find the. So as you can see, these two formulas are the same. It's just instead of x1 and x2, I'm using a and b. So this is how you would find the arithmetic mean of two numbers. This is the geometric mean of two numbers, and this is the harmonic mean of two numbers. Let's use this formula to see how we can get the middle term for the harmonic sequence above. So if we want to find the harmonic mean of the first and the third term, this is going to be 2 over 1 over h1 plus 1 over h3. And this should give us the value of the middle term h2. So let's do it. h1 is 1/2. So we have a 1 and then divided by h1, which is 1/2, so 1 over 1/2. h3 is 1 over 8. So you can plug this in your calculator, or we can use some algebra to simplify it. I'm going to multiply this fraction by, and 2 is 2 times of a harmonic. We should plus 1 over h6, which will give us the value of h4, the middle term. So h2 is 1 over 5. h6 is 1 over 17. So I'm going to multiply this by 5 over 5, and this one by 17 over 17. So 5 and 1/5 will cancel, 17 and 1 over 17 will cancel. So I'm going to get 2 over 5 plus 17. 5 plus 17 is 22, and 22 is 2 times 11. So this reduces to 1 over 11, which is h sub 4. So the harmonic mean formula can help you to find the middle term in a harmonic sequence. Now let's calculate the harmonic mean for all of the 7 data points that we have here. If we do it for all 7, we should get the middle term h4. So this is going to be n over the sum of 1 over x. So we have 7 data points. And this is going to be divided by 1 over, so x1 is this whole thing, which is the same as h1. So 1 over 1/2 plus 1 over 1 over 5 plus 1 over 1 over 8, all the way to 1 over 1 over 20. 1 divided by 1/2. By 1/2 is just 2. 1 divided by 1 over 5 is 5. 1 divided by 1 over 8 is 8. And the last one's going to be 20. So if we were to add these, 2 plus 5, which is 7, plus 8, that's 15. And then that's going to be 15 plus 11 is 20.
Dreaming of a career as a data analyst or a data scientist? 365 Data Science is the...
So let's say we have 2 points, point A and point B. And let's say these 2 points are 800 miles apart. Actually, let's make that 400 miles. And let's say we have a car, which I'm going to use a box to represent a car. As the car travels from point A to point B, it travels at a speed of, let's say an average speed of 80 miles per hour. So it's going pretty fast. Then once it reaches point B, it turns around and it goes back to point A, but at a speed of 50 miles per hour. So it's going 80 miles per hour east and then 50 miles per hour west. And in both cases, it's traveling 400 miles in both directions. What is the average speed of the car for the entire trip? This is traveling 400 miles in both directions. What is the average speed of the car 50 miles per hour west? And in both cases, it's traveling 400 miles in both directions. So it's going 80 miles to point B, it turns around, let's say an average speed of 80 miles per hour. So it's going pretty fast. Then once it reaches point B, it turns around and it goes back to point A, but at a speed of 50 miles per hour. So it's going 80 miles per hour east and then 50 miles per hour west. And in both cases, it's traveling 400 miles in both directions. What is the average speed of the car for the entire trip? How do you calculate the average speed in this case? Would you use the arithmetic mean formula to get an equal weighted average? Would you use the geometric mean formula to get a geometric average? Would you use the weighted mean formula to get a weighted average, or would you use the harmonic mean formula? It turns out that in this problem, you can't use the arithmetic mean formula because the time in which the car is traveling east is not equal to the time in which it travels west. So the weight that you would apply to each speed is different. So the arithmetic mean formula won't work. And this problem, I don't see it has any relation with a geometric sequence, so that's out of it. Now you could use the weighted mean formula and the harmonic mean formula to get the answer. But let's get the answer first using good old physics equations. Distance is equal to speed multiplied by time. Or you could say distance is equal to rate times time. We need to calculate the time first for each segment of the problem. Time is equal to the distance traveled over the speed. If you divide both sides by v, you get d over v for t. So if we were to take 400 miles during the first part of the trip, traveling at a speed of, the car's traveling at a speed of 80 miles per hour, if you divide these two, this becomes 40 over 8, which is 5. So during the first part of the trip, it took 5 hours for the car to go from A to B because the car is moving at a high speed. For the second part of the trip, it's going to take longer because it's moving at a lower speed. So the car is traveling the same distance of 400 miles, but at a slower speed of 50 miles per hour. 40 divided by 5 is 8, so this is going to take 8 hours to make the return trip at the slower speed. So because the time spent during each part of the trip is different, each of these speeds will carry a different weight. So we could use a weighted average to get the answer. Now to get the average speed, we need to take the total distance and divide it by the total time, which it really comes back to this formula, d equals vt. Solving for v, you need to divide both sides by t. So you get that v is d over t. So the total distance traveled, 400 miles east, 400 miles west, that's 800 miles. And the total time is 5 plus 8 is 13 hours. So using good old physics formulas, 800 divided by 13, that will give us an average speed of 61.538, I'm going to round that to 54, meters per second. Now what we want to do is we want to use the weighted mean formula and the harmonic mean formula to get the same answer. So let's start with the weighted mean formula. We know the average x value is going to be the weight times x1 plus the weight of x2 times x2 divided by the sum of the weights. Now the weights could be different things. For the acid mixture problem, the weight was the concentration. For this problem, the weight is going to be the time that the car spends going at the different speeds. Because remember, we want to average the speed. In this formula, we're trying to find the average x value. In this case, x represents the speed. So if we were to replace x with v, we would get the form like this. The time is the weight. So w1 corresponds to t1, and x1 corresponds to v1. So this would be, you could say t1 v1 or v1 t1, the order doesn't matter. So this will be v1 t1 plus v2 t2 divided by t1 and t2. So time is what determines the weight of each speed in the average speed calculation in this formula. So v1 is 80, we're going to multiply that by 5. v2 is 50, we'll multiply by 8, and then we'll divide it by the total time, t1 plus t2, which is 13. So we have 80 times 5 plus 50 times 8, which is 800 divided by 13, and that will give us the same answer, 61.54. Now you can also do it this way too. You can find the average velocity, the average weighted velocity, by taking v1 and multiplying it by t1 divided by the total time, plus v2 times t2 divided by the total time. When you take t1 divided by the total time, you're going to get the decimal equivalent of a percentage. So this tells you the percentage of the total time that the car is traveling at 80 miles per hour, and 3 is by 80 by, you're going to the car about 60. Notice that the average being 61.5, the arithmetic mean being 65. This will be 65. But notice that the average speed is lower than the arithmetic mean. Why is that? Why is the average lower than the arithmetic mean? The average being 61.5, the arithmetic mean being 65. The reason is this car spends a longer time at the lower speed. It spends a shorter time at the higher speed. So the lower speed has more weight. weight in this problem because the car spends 8 hours at 50 miles per hour, but it spends a shorter time of 5 hours going at 80 miles per hour. So because it spends a longer time going slower at 50 miles per hour, the average speed is going to be closer to 50 than it is to 80 because 50 has more weight. It has more time weight in this problem. So that's why we got this average 61.54, which is closer to 50 than it is to 80. It's because 50 has more time weight than 80. So that's why I wanted to express it this way. So you can see the percentage of the time at which the vehicle is going at, the two different speeds. So 61.5% of the time it's going at 50 miles per hour, and 38.5% of the time it's going at 80 miles per hour. So the average is closer to 50 than 80. Now let's get the same answer using the harmonic mean. So here is our harmonic mean formula. And we are averaging two numbers, so n is 2. And this is going to be divided by 1 over h1 plus 1 over h2. But in this case, h is going to be v, since we're averaging the speeds. 1 100. We've seen it. Other applications to what the other applications are, but this is just one of them that I wanted to go over, so you can see it in practice. Now let's talk about a different type of mean, the root mean square. So when I hear the word root, I think of square root. And when I think of square, I think of like squaring something, like raising it to the second power. It turns out that we're going to have both of those elements in this formula. So if you want to find the root mean square of x, if you see RMS as the subscript, that's root mean square. It's going to be the square root of the sum of not just the x values, but the square of those x values divided by n. So when you hear the word root, think of square root. When you think of square, think of x squared. So if we were to expand it, it will look like this. So it's going to be x1. So if you want to find the root mean square of x, if you see RMS as the subscript, that's root mean square. It's going to be the square root of the sum of not just the x values, but the square of those x values divided by n. So when you hear the word root, think of square root. When you think of square, think of x squared. So if we were to expand it, it will look like this. So it's going to be x1 squared plus x2 squared plus x3 squared all the way to xn squared divided by n. So let's say we have 5 numbers, 5, 8, 12, 16, 21. And we want to find the root mean square of this data set. So it's going to be 5 squared plus 8 squared plus 12 squared plus 16 squared plus 21 squared, all divided by n, which n is 5. So let's go ahead and plug this in. Numbers square. So we get this formula for the root mean square. Now let's say if we want to find the root mean square of just 2 numbers. So let's say we just have these 2. Let's say x1 is a, this would be a squared, and x2 is b, that would be b squared. So a squared plus b squared. If we have 2 numbers, n is going to be 2. So we get this formula for the root mean square of 2 numbers. It's a squared plus b squared divided by the 2 numbers, all in the square root. So let's put this together. We know that the arithmetic mean of 2 numbers is basically the sum of those 2 numbers, and n is going to be 2 since we only have 2 numbers. The geometric mean of 2 numbers is the square root of the product of those 2 numbers, with the index being 2. The harmonic mean of 2 numbers is 2 over 1 over a plus 1 over b. Now, there's a different form of that equation. If we multiply the top and bottom by ab, we get 2ab on the top. Here the a's will cancel, giving us b. And here the b's will cancel, giving us a. b plus a is the same as a plus b. So we get this other form of the harmonic formula. So you may want to write this in your list of equations. So the harmonic mean of 2 numbers is 2ab over a plus b. Now the root mean square of 2 numbers, which I'm just going to call r, that's equal, we said it's equal to the square root of the sum of the squares of those 2 numbers divided by 2. Now let's say that a is 10 and b is 20. Let's go ahead and calculate the arithmetic mean, the geometric mean, the harmonic mean, and the root mean square of those 20 is 30. Squared is 100. The highest value. The harmonic mean gives us the lowest value. And so we can rank these 4. So the harmonic mean is going to give us the lowest. The geometric mean, 14.14, that's between the harmonic mean and the arithmetic mean. And the root mean square is going to be the highest. So we have this pattern. H is less than G, which is less than A, which is less than R, over 3. Now 15 is 5 times 3. And when we multiply that by 40 by and 3, the 3's cancel. 5 times 40 is 200. And the square root of 200 is, well, 2 times 100. The square root of 100 is 10. So we get 10 root 2, which we can see that that's equal to G. So that's a formula you can add to your list. The geometric mean is equal to the geometric mean of the arithmetic mean and the harmonic mean. Now from that formula, we can get some other formulas too. So if we were to square both sides of this equation, we'll get g squared on the left, and the square root symbol will disappear. So dividing both sides by a, we get that the harmonic mean is equal to the square of, going back to this equation, or this form of the equation, the square of the geometric. So if you know so all of these different ways of calculating the average all together in one video so you can see how they relate to each other. And I just want to put all of these, for this video, we've covered a ton of different means. And I just want to put all of these different ways of calculating the average all together in one video so you can see how they relate to each other.
Twice, 50 less, going once.
सिग्नेचर जो दूर से नजर आए.
3.
सिग्नेचर जो सबकी सोच से ऊपर जाए.
We have a final bid, 50 crores, sold to the gentleman at the back.
सिग्नेचर जो एक नया स्टाइल बनाए. Signature, a premium product from Dilbagh.
Are you planning to go to Europe this July? Here
That's 50. In this video, we're going to talk about how to calculate things such as the mean, the median, the mode, the standard deviation, the range, and the variance, given about. a bunch of numbers. So here we have these 10 numbers, 15, 27, 74, 36, 8, and so forth. So how can we find the mean, median, mode using Excel? Well, first, let's begin by finding the total. So we could use the sum function to get the total. And we could just highlight, basically, that column of data for Excel. And so that's how you can easily calculate the mean. You can also calculate the mean by taking the average of any set of numbers. It doesn't have to be listed in separate cells. For example, if I want to find the average between 12, 18, 20, and 26, I could just simply enter it into a single cell. And that will give me the average of those four numbers, which you can see here. Now, another way in which will give us 10. And so if we use Excel, so we have 10 numbers, the average, and so 85 is the range. So that's the difference. So the range is going to be the difference between the number, the range, the data, or the number that's found in cell B16, which is 93, minus the number found in B17, which is 8. And so 85 is the range. So that's the difference between the maximum value and the minimum value. Next up, we have the sample standard deviation, or the standard deviation of a sample. So how can we calculate that? Well, to use Excel, type in equal STDEV. So once you highlight that column, you'll get to the squared. So it's the summation. Now let me just use a different color, but point minus the mean. So it's the summation of the square differences between the sample and the mean divided by n minus 1. And all of that is still within the square root. Now let me just use a different color, but with a smaller ink. Now, the formula for the population standard deviation, it looks very similar. Now keep in mind, if you want to find the standard deviation of something, you don't have to. However, you're going to use the population mean. But instead of n minus 1, it's going to be n. And so this is where it differs. Now keep in mind, if you want to find the standard deviation of something, you don't have to place it in different cells like this. For example, if we want to find the standard deviation of the first 5 numbers, 1 through 5, just type in STDEV, and let's use the sample standard deviation, and then 1, 2, 3, 4, 5. And so for the first 5 numbers, it's 1.581. If you wish to calculate the population standard deviation for those first 5 numbers, you can follow the same format. As you can see, it's a little bit less than the sample standard deviation. So let's go ahead and finish this problem. So the population standard deviation for the numbers that we have is going to be 26.5497 with some other numbers. Now, what about the variance? So there's sample variance and there's population variance. So type in equal var.s and then highlight the 10 numbers. And so that is the variance for the sample. And for the population, type in equals. Sometimes I forget to do that. var.p and then select the 10 cells. So the population variance is 704.89. Now, the sample variance is simply the square of the sample standard deviation. So we can get the same answer if we take the data in cell B19 and square it. So make sure you put equal, then parentheses B19, shift 6 to put that little up arrow, and that's how you can raise a number to an exponent and then square it. So as you can see, we get the same answer. Or we can do, to get the population variance, we can square the data that's in cell B20, and that will give us 704.89. And so that's how you can calculate the variance from standard deviation. And that's it for this video. Now you know how to calculate the mean, median, mode, the range, the standard deviation, and the variance using Excel. Thanks for watching. So how can we use the numbers in our data average of approximately 5.95? So that is the mean for this data set. So that's basically it for this video. So now you know how to create a frequency table, and you know how to calculate the mean, median, mode, and range using that frequency table. Thanks for watching.
Moving to Canada made simpler with BMO.
In this video, we're going to focus on making a cumulative relative frequency table. In this video, we're going to focus on making frequency tables and dot plots. In this video, we're going to talk about how to draw a line plot and also how to interpret the data presented in the line plot. So let's go ahead and begin. Draw a line plot given the following numbers. So one of the first things we should do is we should arrange the numbers in ascending order. So let's start with the lowest number, which is 0. So we have 3 zeros. Next on the list is 1. And we have a total of 5 ones. The number line. So let's list of numbers. Now let's work on a practice problem that will help us to interpret the data found in a line plot. Number 2, a survey was conducted asking everyone in a certain 55 and older suburban community how many cars they own. The results of the survey were displayed on the line plot shown below. Now based on the data collected, how many individuals own one car? So on the horizontal axis, we have the number of cars owned. And going up, we have the number of individuals who own such cars. So with this information, how many individuals own one car? So this is the part for one car. What we need to do is count the number of X's that we see here. And that is 8. So we have 8 individuals who respond to the survey, indicating that they only own one car. Now what about part B? How many individuals own at least 2 cars? So we're looking for how many individuals own at least 2 or more were surveyed to be in this community. And so that's basically it for this video. So now you know how to interpret the data that's... So in this video,
output.
Hey there, how's it going? Hey there, how's it going, everybody? In this In this video, we're going to be learning more about indexes. So we've seen basic default indexes in previous videos, but in this video, we'll learn how to set custom indexes and the benefits of doing this. Now, I'd also like to mention that we do have a sponsor for this series of videos, and that is Brilliant.org. So I really want to thank Brilliant for sponsoring this series, and it would be great if you all could check them out using the link in the description section below and support the sponsors. And I'll talk more about their services in just a bit. So with that said, let's go ahead and get started. Okay, so I have my snippets file open here, or my snippets notebook open here, so that we can look at indexes using a simple data frame with a little bit of data. And then we'll see how to use these with our larger survey data set that we've been using so far. So far in the series. So in these snippets, we have the same small data frame that we saw in the last video, where we just have 3 people with their first name, last name, and email address. And I have this data frame displayed down here at the bottom right here. So like I said in previous videos, our data frames have this thing on the far left over here that looks like a column without a name. And this is an index. So since we've just seen these default indexes so far, this is currently just a range of numbers that's basically an integer identifier for the rows. So this is a 0, a 1, and a 2. Now sometimes it may might make more sense to have a different identifier for each row, and that will basically be the label for that row. So it's usually unique. Now pandas doesn't actually enforce indexes being unique, and sometimes it won't be, but most of the time these will be unique values. So what might be a better index for our sample data here? Well, maybe the email address would be a good index for this data, since that's usually a unique value. Force indexes being unique, and sometimes it won't be, but most of the time these will be unique values. So what might be a better index for our sample data here? Well, maybe the email address would be a good index for this data, since that's usually So in these snippets, we have the same small data frame that we saw in the last video, where we just have 3 people with their first name, last name, and email address. And I have this data frame displayed down here at the bottom right here. So like I said in previous videos, Our data frames have this thing on the far left over here that looks like a column without a name, and this is an index. So since we've just seen these default indexes so far, this is currently just a range of numbers that's basically an integer identifier for the rows. So this is a 0, a 1, and a 2. Now, sometimes it might make more sense to have a different identifier for each row, and that will basically be the label for that row. So it's usually unique. Now, Pandas doesn't actually enforce indexes being unique, and sometimes it won't be, but most of the time these will be unique values. So what might be a better index for our sample data here? Well, maybe the email address would be a good index for this data, since that's usually a unique value for most people. So right now, if I wanted to view all of the email addresses, then we could say df and access the email column. And we saw this in the last video, but we can see that it displays all of these email addresses. Now, what if we wanted to set these email addresses as the index for this data frame? Well, to do that, we could just say df.set_index, and then we can just pass in the name of the column that we want for the index. So if I run this, then now we can see that the email is on the far left and it's bold. And it actually does kind of look like a normal column because this index has a name. It has the same name as our column when we set it. So I want to show you something here. We can just set this index in this cell, but if I look at my data frame again, so underneath here, if I say df to print out this data frame, then we can see that our data frame didn't actually change. It still has the default index over here on the left. And that's because Pandas doesn't do a lot of these changes in place unless we specifically tell it to do so. And this is actually nice because it allows us to experiment without worrying about modifying our data frame in unexpected ways. So let's say that we actually did want to set our index to the email column and have those changes carry over into these future cells. So to do this, back up here where we said set index, we can just add in another argument here and say in place is equal to true. Now, if I run that and then rerun the data frame again, then now we can see that it actually did set that index and modified that data frame. And we can actually look specifically at index just by saying df dot index. And if I run that, then we can see that we have an index here, and it has the values as a list of what all the index values are. And it also tells us that the name is equal to email. Okay, so why would this actually be useful? Well, like I said before, the email address as the index gives us a nice unique identifier for our row. And remember in the previous video that we used .loc to search our data frame by label. Well, these indexes are the labels for these rows. So before, we just used the default ranged index, but now we can find a specific row by passing in that label. So if I say df.loc, this will be easier if we actually just look at an example here. If I say df.loc, before we were passing in a 0 as the label. But now I can say, okay, I want to see the information for corymschaefer@gmail.com. And then it'll come back and say, okay, that person has a first name of Corey, last name of Schaefer, and so on. So now we get the row for that specific email index. And like we saw in the last video, we can still pass in values for the specific columns as well. So if we wanted the last name, then I could just pass that in as the second value. So I'll just say I want the last name. And we can see that there we get Schaefer. Now we actually no longer have those default integers as our index because now it's using the email. So if I try to use those integers that we used before, so if I say if I want row of 0 using loc, then we're going to get a type error. And I get an error because it no longer has an index with that label. If you want to use integer location instead of labels, then you still have the iloc indexer available to you. And we saw that in the last video as well. So if I change this to be iloc instead of loc, then it'll still give us that first row. So that still works. Now, if you accidentally set the index and want to reset it, then we can do that with the reset index method. So down here, I will just say df.reset_index, and I will do an in place equal to true so that those changes carry over. And then I'll go ahead and print out that data frame. So if I run this, then we can see that now we're back to having that email as a column and the default range index. Now, if you actually know what you want the index to be, when you're creating your data frame, then you can simply set it there instead of setting it later using the set index method. And we can do that as we're loading in data from a CSV or other source. Other source as well. So let me switch over to our other notebook here with the Stack Overflow data that we've been using so far throughout the series, and we'll take a look at some real-world examples of why using indexes is useful. Now, again, for those of you who have been following along with the series so far, this should look familiar to you. But if you haven't been following along, and this is the first video you've watched, here's a brief overview of what's going on. We are loading in pandas here. We are loading in some CSV files here as well. And I have a link in the description section below to the data that we are using for these CSV files. And then we're also setting some options here in pandas to display max columns to where we can see all the columns, and max rows to where we can see a lot of these rows. And then this is what our data frame looks like. These are just survey results from Stack Overflow. So far, if we look at our data frame here, in the series so far, we've been using this default index, and we can look over here and see that it's just this range from 0, 1, 2, and 3. Now, if we look at the survey response data, then it looks like they actually have a unique value per row within the data itself. So if we look at this respondent column here, this respondent column is actually a unique ID. So it's respondent 1, respondent 2, and 3, and so on. So really, we should probably clean this up a bit and just use that respondent ID as our data frame index. Now, we could do this just like we saw before by coming down here and saying df.setIndex and do it that way. Or we can do this while we're actually reading in the data by passing in an additional argument to the readCSV method. So up here where we loaded in the data, let's just add another argument here, and we will call this index_call is equal to, and now the name of the column that we want to be the index. And in this case, I want it to be this respondent unique ID here. So I'm going to say our index call is equal to respondent. I will rerun that cell. Now I'll come back down here and rerun our data frame head. And now we can see that this is cleaned up a bit because now we have this respondent as our actual index. So now these are the labels. So if you wanted the first respondent, then we could just say df.loc, and that is 1. So this is the first respondent there. Okay, let me delete that cell. Okay, so now let me show you a real world example of where I would use this. So if you remember from earlier in the series, we have our survey data that we can see here, but we also have another data frame that tells us what each of these columns actually means in the survey data. So let me display that data frame real quick. So for example, if I wanted to know what hobbyist meant, then we can look at our schema data frame here, and we can see that the answer that they or the answer on the survey, or the question on the survey for hobbyist, was, do you code as a hobby? So when we see yes and no questions up here for hobbyist, they were answering the question, do you code as a hobby? So here's a question. What if I wanted to locate what a specific column meant without needing to search through this entire data frame manually? Well, in this case, we can simply set the column name as the index and use the .loc indexer. So I'll set this index up here where we loaded in the schema data frame. So let me go back up here to the top, and the column, we want this here to be the index because these are all unique values. So I'm going to grab the name of this column, which just so happens to be column, and then up here, I will say that I want the index to be equal to this column of, actually, let me get that within the string there, okay? Index call is equal to column. Run that, and now let's rerun our schema data frame. And now we can see that that column is bold, so that is our index. So now we can use .loc to search for those columns directly. So if I wanted to see what the information for the hobbyist column was, then I could just say, let me scroll down here, I could say schema data frame .loc, and then we can just pass in the label of the index that we want. So if I wanted to see what hobbyist was, then we can see, oh, okay, hobbyist has the question text of do you code as a hobby? So let's go back to our survey data here and see if we can find a column that doesn't make much sense to us. So if I scroll through these here, okay, like what would this one mean? MGR idiot, okay? MGR idiot. So let me scroll down here, and now I'll paste that in to the schemadf.loc and rerun that. Now we can see that we get the information for that column. Now the text is actually truncated in Jupyter Notebooks by default, but we can change that setting if we'd like to see this entire question text. But I kind of want it on since we have so much data to display. But instead, if you want to see the full text for that question, then you can just access the data in that row and column directly by also passing in the column name into .loc as well. So just like we've seen before, when we're using .loc, this is the row we want. So what column do we want? So we want to read that question text. So I'll paste that in. And now if I run this again, now we can see that the full question text for what MGR idiot means is how confident are you that your manager knows what they're doing? So So this is one nice example here of when setting these indexes is useful because it allows us to make these search these rows by labels very easily, just like we did here with the schema. Now, let me show you one more thing before we finish up here. So we can see that we were able to set our indexes and all of that looks good, but it might make it a bit easier to read this schema data frame if the indexes were sorted alphabetically. So to do that, it's just as easy as saying schema df dot sort underscore index, and let's run this. Let me scroll down here a little bit. And we can see that now these indexes are sorted alphabetically. So if we knew that we wanted to, get to employment or something, it's going to be in the E's. So that just makes it a little bit easier to find what you're looking for. And if you wanted to sort this in descending order instead, then we could just say ascending is equal to false. And now we can see that it is in reverse order here instead. So depending on your data, that might make it easier to read. So we're going to go over a lot more advanced sorting in a future video, but these are just some basics on getting our indexes in order. Now, as usual with our data frame, if you wanted to the sort to be permanent and carry over into future cells, then you should set in place equal to true. And we'll see that a lot throughout the series because doing it this way kind of allows us to see what things would look like without actually affecting the data frame itself. So down here, the data frame is still unsorted. But if I come up here and say sort index in place equal to true, rerun that, and then rerun our schema data frame, then now our schema data frame is permanently sorted. So depending on your data, learning about these indexes will be really useful, especially whenever you're using .loc, because it allows you to search by label there, which is extremely useful depending on what type of data you are searching through. Okay, so before we end here, I'd like to mention the sponsor of this video, and that is Brilliant. Hey there, how's it going, everybody? In this video, we're going to go over the basics of filtering filtering data from data frames and series objects. So for example, if we wanted to look at our survey data and only look at people who know Python, then we can filter that data out. Or maybe we only want to see results from a specific country or people that have a specific salary range, anything like that. We can do all of that by filtering out data from our series and data frame objects, and we'll learn how to do that in this video. So filtering is one of the main things to learn with pandas because it's basically how we begin every project, by filtering the data that we want from the data that we don't. Now, I'd also like to mention that we do have a sponsor for this video, and that is Brilliant.org. So I'd really like to thank you. So let's in just a bit. So with that said, let's go ahead and get started. Okay, so first of all, let me show you something that's going to be the basis for our filters. If we perform some basic comparisons using our data frames, then we'll get back some interesting results. So let's see what this looks like. So right now I have my snippets notebook open that we've seen a couple of times throughout the series. And at the bottom here, I'm going to make a basic comparison and see what the result looks like. So let's say that I wanted everyone that has the last name of Doe from our data frame. There should be two since we have a Jane Jane Doe and a John Doe here in our data frame. So in our bottom cell here, I'm going to put a comparison that says DF, and then we want to access that last name column. And now we can just say if that last name equals Doe. So if I run this, then what we get back is a series object. And this might not be what you expected. So maybe you thought we would just get a data frame back with all of the values that met at our criteria, but what we got back is a series with a bunch of true-false values. Now, these true-false values actually correspond to our original data frame, and the true values are the rows that met our filter criteria, and the false values are the rows that didn't meet our filter criteria. So you can basically think of this like a mask. So we can see here up here in our simple data frame, the last name of Schaefer is false, and these two last names here with Doe are true. So this is a filter mask and when you apply it to a data frame, it will give you all of the rows that meet that filter criteria. So now let's apply this filter to our data frame. So first, I'm going to assign this returned series here to a variable, and I'm just going to call this variable filt. So I'll say filt is equal to, and then this comparison here. Now, filter is a built-in Python keyword, so be sure to use something else. Anytime I assign these to variables, I usually just use this filt keyword here, or not keyword, but variable name. Now, I also usually like to wrap my entire filter in parentheses because I find it easier to read. So this isn't going to change anything, but I'm just going to put this entire thing here within parentheses so that I can see that this assignment here is separate from this equal sign. Okay, so now we have this filter here. And remember that this filt variable here is equal to this series here of true and false values. And now let's apply this filter to our data frame. And we can do this in a couple of ways. So you might see some people do it like this. We can just pass that directly in, like we are searching for a column. We can pass in a filter there. And if I run this, oops, and I got an error there because I did not run this cell to set that variable. So I'll rerun that. And now if I run this, then now we can see that we get a data frame back where it returned all of the rows that have the last name of Doe. Now, we only assigned the filter on a different line because I think that's easier to read, but you might see some people put these comparisons directly in the brackets for the data frame. So you might see something like this. So I'm just going to comment that out right now and just grab this entire filter here. You might see some people do it like this and just paste it or put it directly in there. And we can see that that works too. Now, I think that that's a little more difficult to read than just assigning this to a variable. So I'm just going to use that as a variable, but you should know that it is a possibility since you will see some people put the filter directly in there. Okay, so that's one way of narrowing down those rows. Now, another way that you can do this, and the way that I prefer to do it, is to use the .loc indexer that we've seen a few times now. And I'll talk a bit about why I prefer this in a second, but if we pass in that series of booleans into .loc, then it should give us the same results that we currently have. So if I say df.loc and pass in that same filter, then we can see that we get the exact same thing. This here gave us the same results as our .loc down here. So this is one reason why pandas can be a bit confusing to people, because there are multiple things that you can pass into these different brackets to get different results. So like I said before, .loc is used to look up rows and columns by label, but if you pass in a series of booleans like we did here, then you can also filter data out. Now, the reason that I like using .loc for this is because we can still grab the specific columns that we want as well. So for example, if I wanted the email column, then I could simply say, pass in a second value here into .loc and just say that we want that email column. If I run that, then we can see that we get the emails that match those last names. So remember, the first value to .loc are the rows that we want, and the second value here are the columns that we want. So since I wanted the email column, it gives me a series of those emails where the last name is equal to Doe. Okay, so real quick, let's go over some other ways to filter data out here. So first, let's go over the and or operators. Now, we can't use the Python built-in and or keywords for our filters, so we're going to be using some other symbols. And the symbols that we're going to use here are the ampersand for and. Let me write these out here. The ampersand for an and this vertical bar for an or. So these symbols carry over from other programming conventions, so you may have seen them before. So for example, let's say that we wanted our filter to get all of the rows where the last name is Doe and the first name is John, which should only return this one result. So in order to do this, we can go back up to our filter here, and I'm just going to get rid of this cell here because I'm just going to be using .loc from now on. So now with our filter here, let's say that we want a last name equal to Doe, and, which we're going to use the ampersand, and we want the first name equal to John. So I will put that in here. And I also, let me actually separate these out as well. I like to have each one wrapped in parentheses. I think it makes it a bit easier to read. So now if I rerun that filter and then rerun our .loc, then we can see that now we're just getting that single email address. And that email, again, is where all of the last names were equal to Doe, and the first names were equal to John. So in this case, it's just one result. So now let's look at an example using the or operator. Now for this, we can use the vertical bar character. So let's say that I wanted a filter where the last name is equal to Schaefer or the first name is equal to John. Okay, so if I wanted the last name to be equal to Schaefer or the first name is equal to John, for the or, we're going to do a vertical bar character there. So now if I rerun this, then we can see that we get back all of the rows or all the all the email addresses where the last name is equal to Schaefer or the first name is equal to John. So in this case, it was these two rows here. Now we can also get the opposite of a filter. So let's say that I wanted to get the complete opposite of this filter where we want all of the rows where the last name isn't Schaefer and the first name is name isn't John. Now I could go in here and fiddle around with this query that I currently have, trying to get everything right, or I could simply add in a tilde at the beginning of this filter, and it will give me everything that didn't match that filter. So if I just come in here and put a tilde there, then that is going to negate that filter and give me the opposite of those results. So we can see here that we get Jane Doe because that is all the results where the last name was not Schaefer or the first name wasn't John. So this goes back to truth tables that some of us may have studied in school. Now, if anyone is unfamiliar with truth tables, then let me know and maybe I can make a future video on that subject, but it's more mathematical related than programming related, although the two do overlap very frequently. Okay, so that kind of covers the basics of filtering on a small data frame. But now let's go back to our larger data set of survey data and look at some real world examples of some filters that we might want to take a look at. So I'm going to bring up my other notebook here. And here we have the Stack Overflow survey data that we've been using throughout the series. And again, if you'd like to follow along, then you can find a link to this code and the data in the description section below. Okay, so now that we've learned about some basic filtering, let's see if we can run some filters on our survey data here. So for example, let's say that we wanted to look at the data for people who are making a salary over a certain amount. Now maybe we want to take a look at what languages are earning the higher salaries or something like that. So in order to do that, I'm going to first create a filter. Now, if you don't know which column in the data frame gives the salary, then you can always find that using the schema data frame that we've seen throughout the series that tells us what each of these columns here means. But for the sake of time here, I'll just tell you that the column for salary, if I go over here, I think I can find it here pretty quick. It is this converted comp right here. right here. So if we scroll down through some of these survey results, we can see that this person says that they make about 9,000. This person makes 61,000, and these are converted to USD. And real quick, let me reload this page here just to make sure that I have run all of these cells and that I'm that all of these variables here have been initialized. Okay, so if we wanted to get a filter with all of the high salaries, then let me come over here and again, I will copy this column name here. And now let's make a filter. And I'll call this filter high salary. And I'll set this equal to a conditional here where we're saying that we want the DF of this converted comp column of our data frame. We want that to be over, let's say a high salary is over 70,000. You know, this is kind of subjective, but we'll do that as a filter here. And now let's apply that filter to our data frame. So just like we saw before, I can say df.loc and I can pass in that high salary filter there. And now we can see that we get some results here. And this isn't all of our respondents. We can see that now it's respondent 6 and 9 and 13. So if I scroll over to our converted comp, then all of these salaries here should be over 70,000, and it looks like they are. Now, in order to narrow these columns down a bit, let's just grab a certain number of columns. So I'll grab the country, the programming languages, and the salary. So to do this, remember we can just pass these into .loc. So up here where we're doing .loc, I'll put in a comma here, and now I'll put in a list for the columns that we want. And let's say that we want to get the country. We also want to get the programming languages that these people have worked with. And this here, and like I said, you can look all of these up in the schema, but this is under languages worked with. We can see that this person knows Java, R, SQL, and so on. So I'll paste that in as one of the columns that we want. And also I will get the converted comp. So I will paste that in as well. And now let's run that. Now we can see that we get not only the people who meet this high salary standard filter that we set, but also we're only getting the country, the languages that they know, and their salary. So our filter does seem like it is being applied correctly and that this is working nice. So now that I'm actually seeing the countries here, that reminds me that we might want to do some filtering with multiple values. So for example, my YouTube audience comes mainly from the United States, India, the United Kingdom, Germany, and Canada. Well, that's where the largest percentages of the audience of people who are watching the videos come from. So let's say that I wanted to filter out the survey results here so that I only see the results from those 5 countries that I mentioned. Now, I could create a super long filter up here where I say, if the country is equal to the United States, or if the country is equal to India, or if the country is equal to the United Kingdom, but that would take up a lot of space. Instead, let's just create a list of those countries, and then I'll show you a neat trick that we can do to filter those out. So now up here, instead of using this high salary filter here, I'm just going to make a list of countries here, and I'll set this equal to, I'm kind of a slow typer here, so let me type these out really quick. Okay, so now if we want all of the survey results where the respondents said that they were from one of these 5 countries, then I can simply say, I'll set a new filter here. Actually, let me do that up here. I'll set a new filter, and I'll set this equal to df of country, so where the country dot is in, and we want the country to be in this list of countries here. So I'm going to run that cell, and now let's apply that filter to our data frame. So if I run this, and just to narrow down these results to make sure to where we can see the country right off the bat, I'm just going to only grab the country there. So if I run this, then we can see, okay, we get United Kingdom, United States, Canada, India. So it looks like that applied correctly as well. Now let me show you one more common filter operation that you'll probably use. use a lot. So we can actually use string methods within pandas as well to do some alterations to our data frame, or in this case, to help with a conditional. So let me show you what I mean. So let's say that we only want to look at people who answered that they knew Python as a programming language. So let's see how we do this. So first of all, the column that lists the programming languages that each person said that they know is that language worked with column. So let's see what this looks like. So in this here, I'm just going to grab that language worked with column. Oops, and I spelled language wrong. So language worked with, is that right? Yep, okay. Okay, so we can see that we get some programming languages here, and each different language is separated by a semicolon. So we can't just do a query where we say, you know, if the language worked with equals Python, because the actual value of that column will be any combination of the languages listed on the survey. So one way that we could do this is to instead use a string method and see if Python is within this string of these languages that they know. So to do this, I'm going to rewrite my filter here, and I'm just going to say that my filter is going to be equal equal to, and we want to grab the languages worked with for each person, and then we're going to use some string methods. So I'm going to say .str .contains, and then I will pass in Python. Now also we can see that we have some NaN values here, but not a number. Now we need to also set a fill value for those, or else we're going to probably get an error. So that is part of the contains method here. I can just say NA is equal to false. We're just not going to do anything with those. So let me explain this one more time here. So this filter that we're putting in place here, it's saying, okay, for this column here, the languages worked with, which are all of these results here, we are saying the string in that column, does it contain Python? So that's my filter. I'm going to run that cell. And now let's apply that filter to our data frame by saying .loc, and I will pass in that filter. And now let's also just grab the languages worked with column to make sure that that worked correctly. So if I run that, then all of these results here, or all of these rows that it gave us back, should have Python in their languages known. So we can see that we have Python there, there, there. So yes, it does seem to be in all of these results. Now this one here, number 8, we can't actually see it here, but we have these ellipses here, so it's probably just being truncated here. Now, in my last video, I kept saying that these were being concatenated. I meant truncated. A few people pointed that out in the comments. So yeah, these are being truncated here, so we just can't see the Python value there, but they are there. And I'll probably do a complete video on string methods here in the future, since there's so much more that we can do with these. We can use them to replace text, to split values, and all kinds of different stuff. So it's these string methods are extremely useful in Pandas. So that's a basic overview of doing some filters with our data frames. Again, the key takeaways are that we can do these conditionals here and have them as a filter. And again, let me print out just the filter without applying it to the data frame. We can see that the filters return a series of true-false values. And when we apply that to our data frame, those true-false values basically apply a mask to our data frames where we get all of the true values back and not the false. So if I look down here, we have respondent 1, 2, 4, and 5 as true, and 3 was false. So if I look at my data frame here, we can see that we get 1, 2, 4, and 5, and 3 is not there because that value was false. So that's how filters work. And again, it's an essential part of Pandas because this is one of the first things that we do with our data whenever we are loading it into Pandas. Okay, so before we end here, I would like to mention that we do have a sponsor for this video, and that is Brilliant.org.
Xiaomi 14CV with Leica professional cameras. Make it cinematic.
Speaking to international clients has always been stressful for me for 2 reasons. One,
hey there, how's There, how's it going, everybody? In this video, we're going to be learning how to alter existing rows and columns in our data frame.
How many streams of income do you have?
Currently, I have 2.
Currently 2. How many streams of income?
I want you to develop a different mindset. I want you to go against the tide of the 21st century and develop mastery. I wrote a book. It came out, I think, 10 years ago now, maybe 9 years ago, called Mastery. It is my 5th book. And it's a very, very important book, and I'm going to summarize it for you. I'll just say first that the reason it's so important is a lot of people nowadays are very undisciplined. They think because of their phones and because of technology, they can get whatever they want just by clicking, just by pointing their finger, and it kind of carries over into all aspects of life. And I want you to develop a different mindset. I want you to go against the tide of the 21st century and develop mastery. So how do you do it? There are 6 steps that I lay out in the book. The first step is by far the most important, and it's not by far the most important in the book. It's the most important thing in your life. You master this first chapter, and everything else will fall into place. It's discover your life's task. Discover what makes you unique. Discover what you were meant to accomplish in life, right? Your calling. What that means is, when you were very young, you were a unique person. Your DNA, your experiences in life mark you out as like nobody else that has ever existed in the past will ever exist in the future. You are one of a kind. You were meant to do something in life that reflects that uniqueness. Whether it's in sports, whether it's in music or the arts, whether it's in science and mathematics, whether it's in social and working with other people, whether it's in an engineering sense, kind of abstract reasoning, you have a power, a superpower. It was given to you, a seed that was planted at your birth. And if you know what that uniqueness is, if you're able to hone in on it, now when you're 20 years old and you enter the work world, you have a sense of direction. I love physical things. I'm born for athletics, for sports. All right, now you can follow that path. I want you to develop a different mindset. I want you to go against the tide of the 21st century and develop mastery. I wrote a book. It came out, I think, 10 years ago now, maybe 9 years ago, called Mastery. It is my 5th book, and it's a very, very important book, and I'm going to summarize it for you. I'll just say first that the reason it's so important is a lot of people nowadays are very undisciplined. I want you to go against the tide of the 21st century and develop mastery. So how do you do it? There are 6 steps that I lay out in the book. The first step is by far the most important, and it's not by the past will ever exist in the future. You are one of a kind. You were meant to do something in life that reflects that uniqueness, whether it's in sports, whether it's in music or the arts, whether it's in science and mathematics, whether it's in social and working with other people, whether it's in an engineering sense, kind of abstract reasoning. You have a power, a superpower. It was given to you, a seed that was planted at your birth. And if you know what that uniqueness is, if you're able to hone in on it, now, when you're 20 years old and you enter the work world, you have a sense of direction. I love physical things. I'm born for athletics, for sports. Right? Now you can follow that path, and then eventually in your career, you'll turn that into something larger. Or for me, it was writing, etc. I experimented. I tried different forms of writing, but knowing that that was my life's purpose gave me an incredible sense of direction. In my book, Mastery, I give you all kinds of tips for discovering it. It's a voice inside of you that you're not listening to, but that you can rediscover. Once you find your life's task, you then enter in the second phase, which is the apprenticeship phase, which is the most important in a way. I mean, the first one is the key. The second one is the most kind of critical for your progress. It's the period in your 20s when you're learning various skills. You want to value learning over money. What matters to you is learning as much as you can about that field that excites you, developing skills that you can combine later on when you turn 30 or 32 into something unique and powerful, a business, a startup, a book, any kind of career in science or whatever, right? You need to be developing skills and taking it very seriously, gaining the discipline that will carry you through life. And just think of your 20s as an apprenticeship phase that you have to go through, just like it did in the Middle Ages, like 7-8 years of working diligently. And if it's something that you love, it's exciting. The third thing is actually a part of the apprenticeship phase, and it's what I call working with a mentor. So there are no shortcuts to mastery. There are no hacks. There are no way to cut it down from 10 years of hard work to 2 years. But having a good mentor is the only conceivable shortcut. Finding somebody who has experience, who's made mistakes, who can teach you, guide you, who can say, this is good, this is bad, can help you avoid wasting a lot of time and really give you the focus that is necessary. And in Mastery, I give you clues for finding the perfect mentor. It's generally someone that you connect with emotionally. It's like your second parent, but it's going to be a very valuable relationship. The fourth step is what I call social intelligence. And what I mean by that is you could be so brilliant at what you do. You could have all the skill in the world. You could be technically proficient. You can know coding left, right, and center better than anyone else. But if you're not good with people, it won't matter at all, right? You'll be making mistakes step in the way, which is unlocking your creativity. Once you have learned all the heuristics, all of the skills you need to learn in your particular field, and you're socially aware, you've worked with a mentor, now you're able to take all of those ideas and make something original and creative, to take that energy and do something that no one else has done before. And a lot of people don't do that. They're afraid now. They've learned all the skills, all the things they need to know. But to take that next step and do something different, start their own business, write something new that's never been written before, create an organization that's never been done before, they're afraid of that. They're locked in that apprenticeship phase. They don't want to leave it. They want to stay with the corporation and do what you want. Creativity means I'm going to take all those skills and I'm going to be bold and I'm going to do something new and different. And if you follow the path that I lay out in the first 4 chapters, your mind will start opening up and things will come to you. And I have many stories in there of the beautiful things that happen to people once they enter that realm of starting to be creative with all the major things that they've learned in life. If you take that far enough, if you keep going farther and farther into the creative process, always learning, always being flexible, you will arrive at the ultimate, the 6th step, which is mastery, which I call fusing the intuitive with the rational. You have so much skill, you have so much experience, you no longer have to think. You have a feel for what comes next. You have an intuition. Ideas come to you out of nowhere. If you're playing chess, you see 40 moves in advance in like a flash of a second. If you're playing the piano, you no longer have to worry about your fingers. You're just automatically doing it. Your mind is elsewhere. It's in the flow, right? If you're a scientist, discoveries will suddenly come to you. It's a wonderful, wonderful feeling. It's a sublime feeling. And I give stories in there. Many of us may never reach that level. I know I've had flashes of it, but I'm not considering myself I've attained that level of mastery. But it's an amazing feeling. And I want to inspire each and every one of you to reach that level of mastery by going through those 6 steps, by being patient and disciplined, by being creative and independent, and then finally following it to the end where ideas come to you and you are the master of your field. And so I think the book is designed to lead you and seduce you into following this process. And that is mastery for you.
Xiaomi 14CV with Leica professional cameras. Make it cinematic.
Hello, my name is Brad Heinz. I'm a partner engineer working with the PyTorch team at Facebook. In this video, I'll be giving you an introduction to PyTorch, its features, key concepts, and associated tools and libraries. This overview assumes that you are new to doing machine learning with PyTorch. In this video, we're going to cover an overview of PyTorch and related projects, tensors, which are the core data abstraction of PyTorch, AutoGrad, which drives the eager mode computation that makes rapid iteration in your model possible. We'll talk about building a model with PyTorch modules. We'll talk about how to load your data efficiently to train your model. We'll demonstrate a basic training loop. And finally, we'll talk about deployment with TorchScript. Before we get started, you'll want to install PyTorch and TorchVision so that you can follow along with the demos and exercises. If you haven't installed the latest version of PyTorch yet, visit pytorch.org. The front page has an install wizard shown here. There are two important things to note here. First, CUDA drivers are not available for the Mac. Therefore, GPU acceleration is not going to be available via PyTorch on the Mac. Second, if you're working on a Linux or Windows machine with one or more NVIDIA CUDA-compatible GPUs attached, make sure the version of CUDA Toolkit you install matches the CUDA drivers on your machine. So, what is PyTorch? pytorch.org tells us that PyTorch is an open-source machine learning framework that accelerates the path from first for build types, activation functions, include computation pattern, serving community projects as well, supporting use cases from stochastic processes to graph growing companies like these, and provides the foundations for projects like Allen NLP, the open source research library for deep learning with natural language, FastAI, which simplifies GPU, those zeros, all tensors as 30 by the default random number maybe those one tensor between operations of decompositions and sample multiply the weights by there's a lot of derivative. Ray tracking enables ray tracking. In a later video, we'll show you how to do more tricks with AutoGrad, like you don't need numbers, the NNIST data set, and correctly classify which digit was represented in the image. Here's the abridged version of how it works. Layer C1 is a convolutional layer, meaning that it scans the input image for features it learned during training. It outputs a map of where it saw each of its learned features in this image. This activation map is downsampled in layer S2. Layer C3 is another convolutional layer, this time scanning C1's activation map for combinations of features. It also puts out an activation map describing the spatial locations of these feature combinations, which is downsampled in layer S4. Finally, the fully connected layers at the end, F5, F6, and output, are a classifier that takes the final activation map and classifies it into one of 10 bit network structural simulation in code varies with the diagram above. This demonstrates the structure of a typical PyTorch model. It inherits from torch.nn.module, and modules may be nested. In fact, even the com2d and linear layers here are subclasses of torch.nn.module. Every model will have an init, where it constructs the layers that it will compose into its computation graph, and loads any data artifacts it might need. For example, an NLP model might load a vocabulary. A model will have a forward function. This is where the actual computation happens. An input is passed